K Khorasani, so he's a East Island visitor, so I'm hosting him and doing some great work, and also teaching second pro course in control. And yeah, and it's awesome that you can come here, and I think only for 6 weeks, but it's plenty of time hopefully to do lots of stuff. And this seems really interesting, so thanks very much, Kesh.
Thank you very much, Chris, for your kind introduction. Thank you, ladies and gentlemen. It's my pleasure to be here to present a very brief overview of some of the research work that I've been involved in the past few years. So the title that is announced in the email is a bit longer than what I'm presenting here. As you can see already, I have 71 pages, so I'm not going to expect to cover actually this presentation. If there's an interest and if there's an interest on this topic, I'll be more than happy to present the follow-up or the continuation of this talk, and also go back and talk about another application domain, which is unmanned aerial vehicles and cooperative control of multi-agent systems in another presentation. There's another presentation I have on cybersecurity to be given in 2 weeks' time. So that's so that will be maybe another opportunity for presenting some other results. So the title is basically Diagnosis, Prognosis, and Health Management of Complex Systems. So here is the outline of this presentation. I'll briefly go over some of the activities that my research group have been involved in the past 7 to 10 years. And actually the people who are involved in doing this work. The credit is actually all due to them, which are the graduate students. Then I will introduce a problem. I introduce what is the problem in diagnosis and prognosis. Then I look briefly at an application target, which is the gas turbine for aircraft. And I'll just briefly give an overview of that. And then get into the two main methodologies that we are going to discuss in this talk. One based on model-based approaches. These are conventional mathematical model-based approaches to any kind of a system analysis. And then I introduce a complementary kind of a solution, which I call it as a hybrid solution. And that involves an integration of model-based solutions with machine learning-based approaches. And you will see that, as a matter of fact, this hybrid solution, which is not very common, I have to admit, it's not very commonly done, at least in the literature, provide us with much better performance and results compared to just simply doing a model-based approach, which is quite common, actually. So that will be essentially the contribution that we have in this work. The other two topics on prognosis and health management, I think I will probably leave it for another presentation. As I said, if there's an interest, I'll be more than happy to follow up on that. But I will briefly mention what is the problem of prognosis and health management in my introduction in item 2. But to get into the details and technical work that we have been involved, I will leave it hopefully for another day, if that's okay with you. So just briefly go over the work that I've been involved. So I start with the funding that we have been able to secure in the past 10 years. And that usually, by looking at the funding, usually you can see the focus or the interest and the emphasis of the researcher. So that's what I start with. Actually, 3 of these, the top 3 have been secured in the past few weeks. Actually, one of them while I was in New Zealand. So one is, the first one is a project by NATO in Brussels, dealing with the project on cyber physical system security and resilient control recovery. This is a project funded by the Science for Peace and Security program that NATO has. And it involves 4 universities from 4 countries. It involves, of course, Canada, our group at Concordia. It also involves researchers at the University of Melbourne. It involves people from Hiroshima University in Japan, and also involve researchers from Qatar University in Qatar. So it's a cooperation of 4 universities with 4 different countries. And the target application that we are focusing here, dealing with safety critical system, has to do with smart grid. This is an application that is receiving a lot of attention, hackers are really targeting key safety and critical infrastructure systems. So one application is that. The other application is water treatment centers. And the third has to do with chemical process and process control systems. So those are the three target applications that we are looking at this project. The second one, again, as I said, we just received funding from that. And it's supported by the Canadian Space Agency on this CubeSat project. For those who are not familiar with the CubeSat project, this is again an international kind of a challenge that is going on. And the idea is to build these shoebox sizes, 10 centimeter by 10 centimeter by 10 centimeter satellites. Usually it's basically student driven. It's motivated by the students and driven by the students. And the Canadian Space Agency basically had an RFP, request for proposal, nationally, and they said that they would select one project from each province. Unfortunately, the project that we basically forwarded was selected from the province of Quebec. So there will be 10 projects for 10 provinces and 3 territories. And the idea is once the students build this project or this satellite, then Canadian Space Agency will launch it to the International Space Station. And then from the International Space Station, there's a company that has been hired by the Space Agency to launch it to the orbit. So this is actually a project that the students will be involved in really building a satellite and seeing actually the outcome of their work. So I think this is a once-in-a-lifetime opportunity for our students, undergrads and the graduate students who are involved in that. And there are 2 payloads that this project tries to target. One for hyperspectral imaging, another one for basically fault-tolerant hardware electronic systems in that satellite. The third project is funded by the provincial government in conjunction with Thales Group. This is a major French conglomerate. It's a defense and aerospace company, and deals with the topic that I'm talking today, DPHM, Diagnosis, Prognosis, and Health Management, for Canadian Bombardier's aircraft C-series airplanes. So that's a target for the sensors and actuators that we're going to be looking for diagnosing and prognosing. The fourth project was supported by federal government with a Canadian company called CAE. I'm not sure if you are familiar with that. This company, CAE, is the largest flight simulator company in the world. They train something like 10,000 pilots a year. These are for all the airlines. All the airlines in the world have to have their pilots certified. And the certification process is done at this company, CAE. They have a huge infrastructure there. These flight simulators are as big as this room, maybe even bigger than that, maybe twice as high as this room. If you go inside one of these, it's really an interesting experience because you feel that you are actually in an airplane, and it's really interesting kind of experience. But the project deals with cybersecurity for unmanned aerial vehicles, because not only they train pilots for civilian applications, but they also train pilots for military services. So their interest is if somebody can hack into their unmanned aerial vehicles and basically cause a damage into the system. So we are looking at that target application in this project with CAE. We also had 2 projects from Qatar Foundation. I have to say this country is very generous. Usually countries don't, these are federal or national funding agencies. Usually countries don't send money outside. Canadians' money cannot send $1 outside. I'm sure maybe New Zealand have the same policies. If it is private, you can do that. I mean, if it's a private company, they can invest anywhere they want. But taxpayers' money is very difficult to send outside. Qatar has this policy that they want to encourage research internationally. So we got 2 projects with them where we dealt with one of them dealing with health monitoring and diagnosis, prognosis of the industrial gas turbines. They are one of the major producers of gas in the world. And the other project had to deal with a network of unmanned underwater vehicles where we are interested in investigating oil and gas pipelines. So that was the project that we have with them. There are other projects, but I want to mention maybe two of them. One was with Pratt & Whitney. Again, this company is a major American and international company that builds jet engines for various kind of aerospace applications. And so we had a project with them where we collect data from actual engines. So that was again for monitoring the engine of an aircraft. And we have what I want to mention. We had a project with the Canadian Space Agency, a major project way back, where we worked on diagnosis of RADARSAT satellite. This is RADARSAT-1. It's one of the major satellites in Canada, which is used for Earth observation and communication systems. And we had actually telemetry data corresponding to 8 years. So we're talking about terabytes of data. Within one subsystem of the satellite, the attitude, orbital, and control subsystem. So there were like 250 variables that the operators basically download from the telemetry data from the satellite. And then we had to essentially go through collecting relevant information, features, characteristics associated with failures that happen in the actuator of the satellite. Essentially, you have a reaction wheel, like a DC motor that is responsible for attitude control of the satellite. You had one that failed, so we were looking at the telemetry data to see whether, based on only data, not mathematical models or any other thing, based on telemetry data, whether we could detect the onset of the fault in the system. Actually, we showed that we could do it a month sooner than on-the-ground operators that are monitoring the satellite. And the redundant actuator that was then also failed, so you had not only the primary actuator failed, the redundant one also failed, and we were also looking at being able to detect the onset of that fault that happened in that system. So we worked with the real data, and actually that created a lot of interest, at least for myself and my research group, to be focusing on this domain of diagnosis and prognosis. So this is a very brief overview. Now, all of these projects have, in the past 7 years, have led into graduation of 8 postdocs and a number of PhDs, masters. These are mostly supervised by myself, but there are some co-supervised. Currently, I have 2 postdocs, there's 6 PhDs and 4 masters, and their work has resulted in a number of publications. So with that quick overview, let me just start the presentation today on why we are interested in DPHM, again, prognosis and health management. And the main driving factor that pushes the interest in this domain comes from improving the manufacturers, and this is maybe interested. We are interested here for aerospace manufacturers, but it applies to other sectors as well. Is the interest in increasing their competitiveness and how you can improve your competitiveness. You can do it by reducing the cost, and the cost that we are talking about is cost of operation, maintenance, and even components, or improve the performance, improve the reliability, safety, availability, and all of these other factors. So due to these demands on improving the reliability, maintainability, and survivability, people have come up with more complicated control architectures, with more complex sensors, with more complex actuators. And these increases in complexity essentially resulted in the fact that we have to come up with more challenging and more complex health monitoring, diagnosis, and prognosis technologies. So this has been the motivation for this surge in interest in this domain. Of the DPHM topics that we are interested in, specifically we are looking at autonomous and intelligent. And the rationale for selecting autonomy and intelligence comes from the fact that in order to design an optimal diagnosis, prognosis, and health monitoring system, you need to be able to work with a huge amount of data. As more sensors, as more actuators, and more complex scenarios are envisaged in these complex aerospace systems, the data becomes more and more available. So we have to be able to work with the real data. We have to process, and we have to make decisions based on these real data. And so having an autonomy, having a decision-making process that is not done by man in the loop kind of a thing, is essentially driving the interest in this domain. Second motivation has to do with the fact that if for every small change that you make in any system, if there are small modifications that you make in your system, and if that means that you need to design your diagnosis and prognosis systems from scratch, then this is not a viable methodology or a viable solution. So what we need to make sure is that the solutions that we design will be interoperable across a fleet or across a family of these aerospace systems. So if there are adjustments, these adjustments have to be done autonomously, without, again, human interference, without labor-intensive tasks that the humans will then be involved in doing that. So autonomy and intelligence are the key driving factors for making sure that these complex systems can be processed and can be analyzed more effectively and more efficiently. And as a matter of fact, the ideas that we are getting is from the space, not aerospace, from space, from satellites, because when you launch a satellite as a probe or long distances, you can rely on humans being involved and monitoring them. So many of these autonomy and intelligence have been coming from JPL and European space agencies and many other national space agencies. So we are trying to adopt and try to modify these technologies to fit within the problem that we have here. Just to make sure that we are all on the same page, let me just briefly mention what I mean by the notion of a fault, because that's a key aspect in this presentation. So what do we mean by a fault? Essentially, any kind of an abnormality, any kind of a malfunction, any kind of a degradation that takes place in the system is now designated as a fault. Fault is different from a noise or disturbances. Disturbances, noises are caused by external environmental factors. The kind of the things that we refer to as faults, they are machine-induced. Okay, so they are internally induced kind of a behavior and activity. So it is distinct, it is separate from the noise and disturbances that you may have in the system. Then we classify faults depending on whether it happens in the sensor, whether it happens in the actuator, whether it happens in the component. So there are various classifications that we go through. Then we define different types and different properties. For example, for actuators, we have loss of effectiveness, lock in place, hard over. There are different notions and definitions that we use then for these faults in the actuators. For the sensors, you have drift, you have loss of accuracy. So there are various definitions and various characteristics that then we allocate with respect to the type of a fault that we are dealing with. Okay? So these are all mathematically well understood and well analyzed in the literature for a long, long time. Now, I said topic is diagnosis, prognosis, but when I say diagnosis, I'm referring to fault diagnosis. So what does a fault diagnosis refer to? Actually, fault diagnosis is also, in some literature, they refer to as FDI, as the problem of FDI. FDI stands for fault detection, isolation, identification. So we can lump all of these three functionalities and call it fault diagnosis, just to simplify the notation. But effectively, fault diagnosis refers to first detecting, isolating, and then identifying. So obviously, from the notion of detection is clear, it's a binary decision. Is there a fault in the system or not? So that's the first thing that we have to make a determination. Whatever system you're dealing with, complex system, you need to first make an assessment. Is there a fault in the system or not? If there is a fault, then you need to isolate the fault. So you need to find out, is it happening in a sensor? Is it happening in an actuator? Is it happening in a component? And beyond that, well, if it is happening in an actuator, which actuator? If it is in a sensor, which sensor? And then once you clarify these questions, then you need to worry about identification, which deals with finding out or estimating the type, the severity, the nature of the fault. Again, going back to those classifications that I mentioned earlier, these are the kind of things that you need to make a decision on. So that's the problem of fault diagnosis or FDI. But that's just half the problem. Because once I know that there is a fault, I know where the fault is, I know what is the type and nature, all of that, then the next question is, okay, what do you do about it? What am I going to do about it? If you leave these faults unattended, then they can lead into instability. Not only they cause a loss of performance, but they can also lead to instability of the system. So we need to be proactive. We need to be proactive and take a decision. And that's the problem of fault tolerant control. So then you need to go back and change your control laws. You need to change your control strategies based on the knowledge, based on the information that you obtain in the diagnosis phase. So depending on the type, depending on the location and nature of the fault, then you need to reconfigure, recover essentially your control laws to make sure that you can compensate for these loss of performance to the maximum level that will be feasible for you or achievable for this problem. So these are the general questions that we need to address in any kind of a research in this domain. Now, in terms of requirements that you have for your diagnostic system, obviously what you need to do is to come up with a system that detects the presence of the fault as soon as possible. That's your first objective or your first requirement. Can I detect the fault as soon as possible? The same thing, can I isolate the fault as soon as possible? And then you need to worry about the classification and the rate of classification of your fault. In other words, you don't want to have too many false positive or false negative classification. So we need to do a confusion matrix analysis, as is common in classification domain, in pattern recognition domain. So we need to make a confusion analysis to show that you don't have a false positive. By false positive, I mean that the system that we designed says that there is a fault, but there is no fault actually in the system. And false negative obviously means that there is no fault, but it says that there is a fault. So what you need to do is to make sure that these false alarm rates are as small as possible. Why is that important? Why you need to have a low false alarm rate? Because the next step, which is the recovery, this is extremely important. The next step, which is the recovery, if it is based on wrong decisions that I made in the diagnosis, I can actually make things worse. Meaning that if my system says that there is a fault, and says the fault is in this actuator, then I start a recovery policy or recovery protocol to change the control law. There is nothing wrong with that actuator, but since my method was incorrectly classifying that actuator as having fault, I start recovery procedure when there was no need for that. Actually, that recovery can make it more unstable than the fault that was not there even. So it's extremely important that we end up with a low false alarm rate as much as possible. And if I didn't detect the fault, if there is a false negative alarm that I get, and I leave the actuator or sensor unattended and not recovered, that can lead also into instability and loss of performance. So it's important to make sure that these rates are as low as possible, and that's one of my criteria, as you see in the results that I show, that we're trying to achieve. Now, the problem of prognosis and health monitoring is actually completely different than the diagnosis. In the case of the diagnosis, the problem or the fault has already occurred. Now I'm trying to detect it. Now I'm trying to isolate it. Now I'm trying to identify it. Problem of prognosis, as it's clear, is prediction, meaning there is no fault in the system yet. So at any present time, what you need to do is to collect information from the process and make a prediction. Make a prediction as to how long is it going to take if this degradation, if this change that is taking in the system will lead into a fault. So this is a precursor to the fault. So that's actually a much more complicated problem because it's all probabilistic and it's not a very clear mathematical models that people have for that. So in the case of a prognosis, based on the information at the present time, I am trying to see what people call as two metrics, RUL and TTF. RUL stands for remaining useful life, and TTL stands for time to failure. So at this point, can you give me a prediction as how much more time I can run this machine? If this is an aircraft, how many more flights I can run this aircraft without going to maintenance operation? Or if there is an interest in failure, how many more flights this airplane will fall apart, okay, or will cause a problem. So these are the kind of quantities that you are interested in prognosis. So just to bring this concept of prognosis to real practice, what we are interested in prognosis is to do maintenance. As I mentioned, we need to find the remaining useful life. Well, how do we address this problem of maintenance based on current technologies? For example, in your car, you come with a set of instructions. After 10,000 kilometers, change your oil, change your filter. These are called event-based maintenance or time-based maintenance. It doesn't matter how I drive my car, whether the car is driven in the desert, in the North Pole, wherever, it's fixed. The manual comes with a set of instructions, and we all follow it. Well, what's the problem with that? The problem is that if you don't need to change the oil, because I was operating in a tropical environment, so there was no pollution, nothing like New Zealand. So there is no need for you to maintain it after 10,000. Maybe I can go to 15,000. So you are going to spend money on maintenance when there was no need for that. On the other hand, if I'm let's say working in some polluted environment, then 10,000 is not good enough. Maybe I should do the maintenance at 5,000 kilometers. So this is the dilemma that we have. Well, through prognosis and health monitoring, we come up with what is called as condition-based maintenance, CBM, condition-based maintenance, meaning based on the information that you're collecting here, based on the information that I'm collecting here, give me a prediction how many more kilometers I can run this car before I have to take it to maintenance. And some fancy cars or luxury cars actually have those kind of a sensor. So they essentially measure the viscosity of your oil and foreign particles, and based on that they tell you that this is the amount of kilometers that you can run without changing your oil. So luxury cars are actually coming up with these kind of technologies. So that's the whole idea, that we need to do maintenance based on the condition of the system. By the condition of the system, then I need to know what is the degradation level, what is the propagation of the fault, what the nature of the change that is taking place in the system is evolving. So broadly, diagnostics and prognostic methodology can be done in two frameworks. One is hardware redundancy, and the other is analytical redundancy. Hardware redundancy is very common, it's very simple, but it is not feasible for all systems because of cost consideration, because of weight consideration. So hardware redundancy says, okay, for every actuator, for every sensor, just add another redundant one. And this is possible, or this is desirable for space application. When you send a probe, because you don't have a maintenance guy along with the probe, so you need to make sure that there is a redundancy. Again, RadarSat-1, the Canadian one, had a redundant actuator, because you can't, once you launch it, you can't go and grab it and service it. Of course, these are projects that people are looking at to do, but it's not very common. So you do redundancy as much as possible, hardware redundancy as much as possible, but this is not a solution that you can adopt for every problem. So most people and researchers are looking at analytical redundancy. What analytical redundancy says is that based on the information that you collect from the process, then we design a diagnostics method, design a diagnostics algorithm, such that the solution of this diagnostic algorithm will tell us the condition of the system. It will tell us whether we have a fault, whether we have what kind of a fault, what's the nature of the fault, and all of that information then can be assessed by processing information from the system. So that's basically the idea that we are trying to adopt here as well. The key idea behind this diagnostics and prognostics is notion of residual generation. This is so critical. Basically what it boils down to is defining an error signal. And that error signal is obtained from measuring the actual signals from the process, comparing it with an estimate of those measurements. So that's what the residual signal means. It's a difference between actual measurements and estimate of those measurements. By looking at this residual signal and the behavior of that, we can detect the fault, we can isolate it, we can identify it, so we can do all of these problems that I mentioned earlier. Now, the methodologies that are available in the literature are divided, as you see here, in three categories. Model-based approaches, these are very conventional. This is majority of the work in the literature focuses on the model-based approaches. So you start with a mathematical model of the process, and then you develop your algorithms based on those mathematical models. The advantage of this method, the approach, is that there's a whole history of knowledge in any physical system. If you go to aircraft, to cars, what have you, there's a knowledge base, there's a huge knowledge base that we can rely on. So these models have been tested, validated, and verified So we can rely on that. So that's an advantage. The disadvantage is that as an engineer, we tend to cut corners. As an engineer myself, we always try to find a shortcut. So we simplify models. We ignore elements. We want to come up with the simplest possible model. So as a result of that culture or policy, you end up with systems that may not represent the full dynamics of the process. So you end up with a lot of unmodeled dynamics, things that you have ignored, but maybe at some point they become significant. So if these unmodeled dynamics and these uncertainties are present in your system, then how can you ensure the reliability and performance of your diagnostics methodology? So that's a drawback associated with model-based. To address this, some people way back come up with this data-driven or machine learning-based ideas. So they said that I don't need any mathematical model. Actually, we work with, sometimes you have no choice but that. We work with a company called, I'm getting old. Sorry, I will come back. It will come to me. There's a company that works with a satellite that is built by Boeing. Okay, it's an American satellite, but it is sold to a Canadian company. Okay, so this is a Canadian company. So we were looking at finding faults in their XIPS thrusters, Xeon-ion propulsion thrusters. So we asked them, okay, can you give us a mathematical model of this thruster? They said, well, there are ITAR issues. Even for Canadians, we can't share this information with you. It's Boeing. They don't share anything with anybody. So, well, they can't stop the telemetry data. So we had no choice but to work with data because we didn't have access to the mathematical model. Of course, these models are there, but they didn't want to share it with us. Anyways, so the idea here is that if I don't have a mathematical model, I still have data that I can generate from the sensors in the process. So just work with the data and try to extract features and information from that. So this is the advantage. The disadvantage of data-driven based methods is that you cannot guarantee that all, again, as far as this diagnostics problem is concerned, you cannot always guarantee that the data that you have will correspond to all fault scenarios that you see in the real life. For example, I have an engine of an aircraft that I want to monitor its behavior. Well, it is supposed to be flying. Okay, can I go and inject some faults in the engine of a plane, real engine of a plane that is flying, and say, okay, here is a fault in this component, so collect the data. That data is corresponding to faulty scenarios. No one will let you touch that, right? This is would be crazy, I mean, if they let you. So, so what I'm saying is that there is a limitation on the data that correspond to those features that are of interest to us. We cannot always expect that the data that we have will represent those scenarios. So that's a disadvantage. And here comes the hybrid solution, which is essentially a compromise between these two. It tries to take the strengths of each of these methods, put them together, and come up with the most reliable solution. And that says that integrate, fuse your model-based approaches with data-driven based or machine learning-based approaches, and hopefully you're going to get a better result. And that's the thesis that I will present here today with the results that actually confirms that having a hybrid solution will get you a much better performance than other methods by themselves. There are many methods in the diagnostics. As far as the model-based approaches, you have nonlinear filtering methods based on Bayesian methods. You have estimation-based, parameter estimation-based methods, and then you have state and parameter estimation-based methods using common filters, unscented, extended common filter, cubature common filter. You have all these ranges of filtering methods that people have developed depending on the complexity of the problem that we can use for model-based approaches. For data or machine learning-based, you have, of course, neural network, fuzzy genetic, and these methods are also used. And then the third branch, which is the hybrid approach, essentially tries to pick and choose, okay, let's pick maybe a common filter with a neural network, or let's pick a parameter estimation method with a fuzzy system. And you see a lot of work in the literature where It's not random, it's not just flipping a coin, but by some logic and by some analysis, people have found the right match between model-based and machine learning-based approaches. And this is one of the things that we are going to show and present in this talk here. So I'm going to skip all of that. So this is basically the outline of the remaining few minutes that I have to present, which has to do with first developing a model-based approach. I'm going to develop a model-based approach for doing diagnosis for a gas turbine. And then second, I'll come up with a hybrid approach, which integrates that model-based approach with a dynamic neural network approach and shows that by that integrated solution, we can do much better performance. We can get much better performance than we could do with a model-based approach. This is a very brief overview of the gas turbine. It's a highly complex nonlinear process. You have to go to thermodynamics, fluid dynamics, conservation of energy. You have to go through all of that to write down the equations of motion, which is highly nonlinear and complex. But the important thing is that there are three basic components: the compressor, combustion chamber, and the turbine. These are the three segments or sections of the turbine that is of interest to us, and we focus on these. You can see here on this slide the effect of degradation that takes place in the system. There are physical problems, erosion, corrosion, fouling, and dirt buildup. These are the causes of degradation that takes place in the engine. The effect of these physical factors cause degradation in efficiencies and mass flow rates, which indirectly impact different temperatures, different pressures, and the speed of the spool or the shaft that have manifestation. So by looking, so this is the idea now, by looking at these signals, by looking at the spool speed, by looking at the temperatures across the turbine and combustion chamber and other components and their pressures, I am trying to see whether these kind of faults or these kind of anomalies take place in terms of efficiencies or mass flow rates. And then once I identify the nature of them, I try to see how to come up with the policy for maintenance. So in terms of maintenance policy, if you need to wash the engine, if you need to change a part, then how that information would then translate into condition-based maintenance, as I alluded to earlier. So I am going to skip all of that. So basically, the idea is, the basic idea that I have for this part, model-based idea is this. So here is a mathematical representation of the nonlinear model of the engine, okay? No one knows these models, okay? But it exists. These are exist. But some people have come up with high reliability or high fidelity representation of these models. So we have these functions f and g, okay? So some approximation of them. But we are not going to use these nonlinear functions f and g in our design. Instead, what we are going to do is we come up with another nonlinear function f and g here. So this shows the mismatch, or this shows the uncertainties and the simplification that you can do from the actual engine to a nonlinear mathematical model that you have. The effect of the degradations that takes place in the system is represented by this quantity h, which is essentially a function of nonlinearities of the system and some parameters, which we call them as health parameters. So the health parameters are those mass flow rate and efficiencies that I showed in the previous slide. So they represent the health condition of the process. So what we are trying to do is actually estimate these health conditions. Now, of course, we are not going to be working with this nonlinear system. We have this model, which we call it as onboard engine model. This nonlinear model is actually available in the flight management system. It's actually used also for controlling the entire aircraft as well. So this model is not something that people don't have. All the aircraft producers and manufacturers have these mathematical models, and they are already coded in the flight management system. So what we have shown, and here is the idea, what we have shown is that if you take a linear representation of that mathematical model of the engine and apply a linear Kalman filter or linear state observer approach and simply subtract the onboard engine model, which is a nonlinear model of the system, from the estimates that you get from your linear Kalman filter, really significant improvements can happen. This was too good to be true when we first, well, not myself, but my students first came up with this idea. It was actually too good to be true, because with this simple trick, it's highly unlikely that you can get this kind of a result. Well, we have the results to actually verify and prove that. So basically what we do is now you have an estimate of the output, and that's where the residual error is now defined. You get an estimate of the output, you have the actual output. These are the sensors that you have in the engine. There are 5 sensors that I have in this engine. So you take the actual from the estimate, and then you generate this residual signal. This is your residual signal. Then you construct the covariance matrices. Then you go through several steps, constructing likelihood functions. Then you find the weighted normalized weights. Then you fuse the residual signals and the covariances, and then come up with a conditional probability and the mode probabilities. Based on the mode probability that you have here, you can see which kind of a mode corresponding to the failure that you have or faults that you have are taking place in the system. So I'm going to skip all of that. So I'm going to show you some results here. So in this slide, what you see, you have 5 sensors. These are the sensors that I have in the engine. You measure the compressor temperature and its pressure. You measure the turbine temperature and pressure, and you have the spool shaft speed. So these are the 5 measurements that I have. What is shown in these 3 columns correspond to different flight modes. So just to simplify our problem, we looked at 3 flight modes. The first one is takeoff, the second is cruise, and the third is landing. Okay, so they correspond to different dynamical behavior of the engine. And here what we are doing is that we are showing the errors in our estimation. So if the estimation error in the mass flow rates and in the efficiencies, if the estimate of the errors in these degradations are high, too low, then we want to see what will be the impact on how soon or how late you are going to detect. So the numbers that you see here corresponds to the detection time. From the point that you inject the fault in the system, how long is it going to take for you to detect? Recall that I mentioned one of the main design requirements is to minimize, or to find out if we can minimize the detection time. So you can see overall, in summary, that the detection times become least in the cruise mode of operation and becomes the largest in the takeoff. This again is intuitive. This is not a big surprise, because when you are at the cruise, more or less the system dynamics is vanishing. You are at a steady state. So the effect of nonlinearities are really diminished. So the linear model that we have would be a good representation of that environment. So that's why we can get good detection times. However, in the takeoff, where you go over the maximum range of operation, the nonlinearities will be more dominant. Therefore, the reliability of your linear model will be more questionable. That's why you end up with the larger detection times as opposed to the cruise. And also, as you can see, as the error in the estimation of the degradations decreases, then the time in detection also decreases. You can also do a confusion matrix kind of a thing here. We did 50 Monte Carlo simulations for each kind of a fault in each of the sensors. And you see, for example, in here, these off-diagonal terms give you the misclassification. So there are 12 scenarios that the system says that there is a fault in the turbine temperature, but in reality there was a compressor temperature fault in that sensor. So ideally what I like to have is purely diagonal matrix with 0 off-diagonal, so that I have a perfect classification. But that's not always possible. Here is another result which shows this: when the severity of the fault increases, and again this is intuitive, when the severity of the fault increases, the detection time decreases. When the fault is more severe, it's easier to detect. Because the problem in diagnosis is not when you have a significant level of fault. If your motor stops working, anybody who's monitoring it can say, oh, there is a fault. There's no current, there's no torque, there's nothing. It's not a rocket science to do that. But the challenge sorry for that Freudian slip here. Sorry, I didn't mean. But the challenge is when the fault severity is low, can you detect it? That's the Achilles heels in diagnosis. If the severity is too high, many methods, I mean, just monitoring signals, you can detect it, okay? This is the summary of this part of the work. It says, it shows in this table, I'm comparing the detection time of 5 methods. Our common filter approach that takes care of the linear filtering and the onboard engine model versus linear common filter, which does not take into account that onboard engine model. Then the extended, which is one level higher complexity of the filter. Some nonlinearity information is incorporated. Then extended, unscented, and cubature common filter. These are much more complicated nonlinear filtering. And to our surprise, our approach gives us the least detection time. So this is not expected. We would expect that the nonlinear methods, and if I tell this to anybody, of course a nonlinear method should do better than your linear approach. Well, here are the results that shows that this is not the case. My thesis or my understanding or my explanation would be why is that in these nonlinear filtering methods, there is no guarantee of convergence. There is no guarantee, in contrast to the linear common filters where there is a proof of optimality. In these nonlinear filtering methods, there is no proof of optimality. So it depends on the scenario, depends on the condition that you have. So sometimes you may actually see that your filters will not converge or will not converge to the right solutions. And here are plots showing the mode probabilities. I think maybe that's more illustrative here. What this shows in this figure here, I have a fault that I have injected at time 250. So before 250, the mode or the condition of the system is healthy. And that's the mode probability 1 in blue. So based on my method, the hybrid method that we have here, you see that when the system is healthy, when the physical system is healthy, it's actually declaring the system to be healthy. Then at 250, there is a fault that we have injected. So there is a switch in the mode probabilities, and after a few short period of time, it switches to the new mode probability, which is P2, which is the correct mode that we have. On the other hand, if you simply use the linear common filters, you see even during the time when the system is healthy, your mode probability, which is associated with the healthy, starts to decrease. At some point, it's going to cross another mode probability 4. So this is a misclassification. This is a false positive kind of a classification that your linear filtering is telling you. It says that there is a fault here, whereas we know that up to 250 there is no fault. And worse, well, not worse actually. So, but after 250, when there is a fault, it actually properly classifies the mode. Other methods, even nonlinear methods, none of these methods can actually detect the right mode probability. So with that, what we said, well, we are not happy with this even. So can we do better than that? And this is the gist of the idea of hybrid solution. And this is not normal. I have to admit that this is not conventional. It's not conventional. It's not a conventional way people design machine learning solutions for dynamical system problems. So what we have the actual process engine. Then we have this mathematical model of that, which is your, could be your onboard engine model or whatever mathematical model that you have of that system. So what we are doing is we're taking a difference between actual engine data, actual system data, comparing it with the data that you generate from your mathematical model. Take a difference of these two. What would be the difference of these two signals? The difference of these two signals represent the unmodeled dynamics, what was not modeled. What was not modeled here, but it is present in the system, will then be manifested in your unmodeled signal. Then we use this unmodeled signal to train a neural network, and this is where it's not conventional. We use the unmodeled signal to train this neural network. So this neural network function is, this neural network function is to capture and represent the unmodeled dynamics. This is not conventional. Conventional thing is design your neural network to capture the dynamics of the process. We want to have a manifestation of the dynamics of the process implicitly represented in this neural network. This is not what we are doing. We are doing completely orthogonal or dual to that. We want this neural network to function as representing the unmodeled dynamics. This is what we do in offline. But when we want to use it in online, we take the actual system, put in parallel with that the neural network, take a difference of the real signal from the process and the signal that the neural network generated. The error between these two signals is what? Is the actual nominal representation. What's the big deal? This diagnostic system that I designed was based on what model? This model. So to make sure that my diagnostic system will not have any false alarms and false classifications, I want to make sure that this diagnostic system is operating with the data that has removed the unmodeled dynamics. So it is operating as if I'm just applying it to the nominal system. If that diagnostic system gives me a perfect result or highly acceptable result for the nominal model, then when I'm applying it to the real system, it should give me the same result that I was able to generate based on the mathematical model. So this is a different perspective and viewpoint that we are proposing in this problem. So when it comes to this engine problem, we use a neural network to generate an estimate of the unmodeled dynamics, take a difference from the engine signal from the sensors and the unmodeled dynamics estimate from a neural network, bring it here to our diagnostics, but we also have our onboard engine model. That information is also used in the filtering. So the unmodeled dynamics estimate is essentially trying to estimate this, which is the difference between actual engine signal and the onboard engine model signal. So that's the neural network job to estimate that. Then the signal that your filters are operating on are generated from this signal. Okay. And I will not go through the details of how we develop these things. I'm just going to close with a couple of slides. And then maybe I can entertain some questions. So here you see the results that we get when there is no fault in the system. And when there is no fault in the system, the mode probability should be healthy, which is perfectly fine. And this is the result with this hybrid solution, neural network and model-based. This is a solution that you get without the neural network put into the system. This is a solution in the first part 1 that I just mentioned. So you see, even when the system is healthy, and even this method that I claim to be so good with this simple modification of onboard engine model gives me a lot of false alarms. So this is even not good enough. Whereas with adding this neural network, we get a very clean kind of a classification. And to make it even worse, showing the difference between my previous model-based approach and this hybrid approach, you see in terms of the true positive and false positive, you see my previous method end up with almost 95% false classification, whereas the true method, the hybrid method that I developed is actually operating in almost a perfect kind of a situation. So this is significant improvement over the previous methodology. And with this slide that I close, this actually now tries to quantitatively show the improvement of this HNN HKF, which is my neural network and hybrid solution, versus my previous method, the model-based approach. And you can see that in some cases, the detection times is shortened by a factor of 10. This is a significant improvement in the performance between my previous method and this new method, which is the hybrid method. And the previous method, even in some cases, cannot even detect, and it can give a false detection. So overall, this method significantly improves the performance of our diagnostics solution. So basically, to summarize, in this research work, what we have done is by a simple, and it's not very intuitive that you can accomplish this goal, by a simple modification to a linear filtering method, by subtracting a mathematical model that is nonlinear. From the estimates of the filters that you generate, you can show an improvement over even nonlinear methods, over the methods that are purely designed from the outset from a nonlinear mathematical representation. So this is completely surprising to us. And to beat ourselves even on that, we said, well, we are not happy with that. We want to do even better. So here is this hybrid solution that says, if you integrate this neural network that is designed to not model the dynamics of the system, but model the uncertainties, the unmodeled dynamics, then we can show even a much more significant performance improvement. So that's a summary of this part of the talk. So there is a second part, but it deals with prognosis, and obviously I don't have the time. I'm already past my time. I appreciate your patience, and I'm sorry if I spoke too fast. But if there are any questions, I'll be more than happy now or at any other time. I'm here for next month, for the entire month. So if you see me across in the hallway, feel free to grab and say if there is any questions. I'll be more than happy to answer. Yes, please.
Yeah, you've assumed additive Gaussian noise. How valid is that for this?
How about?
How valid is the assumption that you've got
Well,
Gaussian noise?
yes, the noises are not Gaussian. So actually, in these cases, the noise do not enter in a linear fashion. So as a matter of fact, you have non-white representations. So when we go to the nonlinear filtering, and that's one of the advantages that the unscented and particle filters try to advertise or try to introduce, is the fact that this linear Gaussian assumption is no longer required. So even if you have a non-white noise, these methods are able to handle, whereas the common filtering methods, linear common filtering methods, will not be able to handle. So of course, in real life, things are not as nice and as clear as we do in simulations, but people have demonstrated, people have shown these results, and to a large extent, they seem to be valid. But if you are trying to be more accurate and more realistic, then you have to remove these assumptions. But the methodologies have, not our methodologies, because it's based on linear Gaussian representation, but the unscented and the particle filters do not require that. So in other words, we have investigated.
But it's still an additive noise model, though.
Yeah, but not a Gaussian distribution. So it's not linear. It's not essentially in a linear fashion. It shows in a multiplicative fashion. So it's much more complicated stochastic process that we can develop and model for those scenarios to address those kind of realistic situations that you're looking at. Yeah. But there's machinery. There is mathematical machinery available to handle those scenarios. But for the kind of a work that we try to do is plain vanilla kind of a solution, basic elementary, which is linear Kalman filters. Obviously, when I say linear Kalman filter, then those non-Gaussian distributions are not going to be applicable. But there are other methodologies that people have developed to address that kind of a scenario. So I'm not sure if that's...
So I'll talk to you after.
Okay. Yes.
In the way you've got using a neural network to take off the unmodeled components.
Yes.
Aren't you vulnerable that if there's a fault which is affecting the unmodeled components, it's going to go through and propagate through to your fault detection?
Yes, that's a valid question, but this is done for healthy systems. So we don't. This is done offline. See, it's an offline training. So offline, we assume that you have a healthy system. So you don't have those faults, you don't have those anomalies, those degradations. So the scenario that we're trying to capture is essentially intrinsic to the process, not due to machine-induced anomalies, but anything that is unmodeled and intrinsic to the process, but healthy process. So that captures the unmodeled dynamics. In this case, now I don't know when there is a fault or not. This is real life. This is online. So now, if the system has a fault in it, I have developed a methodology here to detect and isolate and classify that fault. So, but this neural network first tries to remove from the process those unmodeled dynamics that are distinct from faults. These are two different characteristics that we're looking at. I mean, you may argue that they are coupled. Somehow there is a coupling, of course. It's not perfect solution, by the way. The idea is not to come up with perfect solution. But yes, there is a coupling effect that you then have issue with, because when there is a fault in the system, that fault can impact the unmodeled dynamics in a complicated fashion. Then you are right. Then this will not be a reliable, maybe, or perfect. I would say it's a reliable, but it will not be a perfect kind of a solution that tries to capture that unmodeled dynamics. So there is some error. There is some error still available or possible in this scenario. But it is better than just not having this and taking your model-based approach to the process, because you have a much more opportunity for error in these two processes than you would have in this scenario. But that's a good point, yes.
We're out of time, so yeah, but thanks for us again. We'll have some coffee and get more questions after.
I can go for another 2-3 hours. I mean, I'm charged up. In one day I had 4 hours of lectures.
Coffee over